Okay, so now we're familiar with the t-distribution and how to calculate a t critical value. Let's see how this fits into a hypothesis test. So in this question, we're told that the shopkeeper sells jars of jam. The weight of the jars of jam are normally distributed. It's important to know it's come from a normal distribution with a mean of 150 grams. A customer complained that the mean weight of 8 jars that she's bought was only 147. An estimate for the standard deviation for the weight of those 8 jars was 2 grams. So this was an estimate of the standard deviation. The standard deviation of the population is unknown. The variance of the population is unknown. And we have a small sample size of 8. These are the reasons why we'll be using the t-distribution. We're asked to do a 5% significance level hypothesis test, whether or not 147 is significantly less than the quoted, the stated, the mean weight on the jar. Okay, so let's start how we would usually start a hypothesis test. We need null and alternate hypotheses. The null hypothesis, everything is as it should be. It's the status quo. The mean is 150 grams, just like it says on the jar. The alternate hypothesis, this is coming from the customer, is that the mean weight is actually less than 150. We know our end value is 8. I'm going to collect all of the values we might use in our calculations. The mean from the sample is 147. The sample standard deviation is 2, and the significance level is 5%. This is a one-tailed test, so we'll go with that 5%. Okay, degrees of freedom, 8 minus 1 gives us 7. So just looking at this on the diagram, here's the 8% in the left-hand tail, and our critical value we can find by using the tables. So it's going to be t, 7 degrees of freedom, 5%. That's going to give us positive 1.895. But we appreciate we're on the left-hand side, so it should be a negative z-score. We have negative 1.895. Okay, so when we calculate our test statistic, anything within the shaded region, anything less than negative 1.895 is going to be a significant result. We'll reject H0, will be in support of the customer's claim. Let's calculate that test statistic. So the t-value we have for our test statistic is going to come from x bar minus mu over s over root n. Okay, just substitute the values that we know. This should be an x bar, so that's going to be the 147 minus 150 over 2 over root 8. Okay, that's just going to go straight into the calculator. I'm not trying to do anything fancy. Into the calculator, we get negative 4.2426. Well, that is going to be in the critical region. It's going to be over here. This is a significant result. Okay, just make your comparison, your numerical comparison, as you usually would. Negative 4.2426 is less than negative 1.895. It's in the critical region. We have a significant result. Okay, from here, let's make a couple of conclusions. One conclusion is going to be mathematical, so we're going to be talking about H0. And the second conclusion is going to be in context. We're going to be talking about the weight of these jars. So there is sufficient evidence to reject H0, and we can say there is evidence to suggest or evidence to support that the mean weight is less than 150 grams, and the customer does have a valid cause for complaint. There I've incorporated part B of the question asking us to discuss whether the customer does have cause for complaint. We can talk about this further and talk about the fact we have a small sample size and maybe we should take a larger sample or another sample to see whether or not this cause for complaint is genuine. You know, it's always risky to make decisions off of a small sample size. So potentially increase the sample size, take another hypothesis test, but according to the data that we have at this moment, yes, the customer does have a cause for complaint. Okay, let's have a look at another example. So here we have a concrete manufacturer. So let's be on the lookout for indicators to use the t-distribution hypothesis test, a t-test. Firstly, we are looking for an unknown variance. If we have an unknown variance and we have a small sample size and we know that our sample has been drawn from a normal distribution, then we can go ahead and use the t-distribution for the hypothesis test. Okay, reading through. A concrete manufacturer tests cubes of its concrete at regular intervals, and their compressive strength in newtons per millimeter squared are determined. The mean value of the strengths is required to be 0.47. Any lower than this, and it's a problem. A new supplier of cement offers to supply the firm at a cheaper rate, okay, so they're going to be getting a deal on the price, than their present supplier, and a trial bag of cement is used to make 12 of the concrete cubes. Okay, after testing, they realized that for the sample, the strengths have these summary statistics, the sum of x squared. Assume that the strengths are normally distributed. And from there, we're asked to do a hypothesis test, whether or not the new cement has altered the mean strength of the concrete. Okay, so cement is one of the ingredients in making concrete. I think it's cement, sand, and water. Okay, so is this going to be a t-test? Where we do not know the population variance. So that's one thing ticked off for the t-test. We know that the sample has come from a normal distribution. Okay, so that's 2 for the t-test. And finally, we have a small sample size. There was only 12 concrete cubes made. So all of these 3 indicate to me we should be doing the t-test. Okay, let's get going. So as always, we'll start with the hypothesis. The null hypothesis is that things are normal, things are how we expected them to be. Mu is going to equal 0.47. And for the alternate hypothesis, the question has asked to see if it's altered the strength. So has it increased the strength? Has it reduced the strength? So we're doing a two-tailed test. Mu is not equal to 0.47. Okay, let's just gather all of the variables, the statistics we might be using. So the sample size, n equals 12. We need to calculate x bar for ourselves. It's going to be the sum of x over n. So 5.52 divided by 12. That gives us 0.46. And we need to do a similar thing for our sample standard deviation, for S, the unbiased estimator of the standard deviation. So for S, it's going to be the square root, and here's the formula I like the most, n over n minus 1, sum of x squared over n, minus the mean squared, and then we'll just substitute our values in. Okay, always want to show this for the examiner so they know where the numbers have come from, and to get partial marks if we've made an error. Substituting this all in, and then into your calculator, and just be careful that we're calculating s rather than s squared. Into the calculator, 0.0160. We are doing a two-tailed test, so that significance level of 5% is split in 2, and we've got 0.025. Degrees of freedom is 1 less than the value of n. That gives us 11 degrees of freedom. For these two tails, so these shaded bits of the two tails are going to have the same critical value, except one is positive, one is negative. So the value we look up in the tables, we want the positive and the negative version of it. So it's going to be t with 11 degrees of freedom, and we'll look up 0.025. And from there we get 2.201. So positive and negative, let's put them both in the diagram. When we calculate our test statistic, any value that is in this shaded region is going to lead us to reject H0. It's going to be a significant result. We're going to reject H0. So let's calculate our test statistic. So T, we're going to calculate from x bar minus mu over s over root n. Substitute all these values. We found everything that we need. The 0.46 we calculated. The mean, mu, is given to us in the question as part of our hypotheses. S we calculated, and n was 12. Okay, so just into your calculator. Don't try and do anything fancy with rearranging fractions. Just into the calculator, and we get negative 2.165. Is that significant? Negative 2.165. It's just outside that significant region. It's just outside the critical region. So no, it's not a significant result. Okay, so let's make our numerical comparison. Our value was bigger than the critical value. This is not significant. And as always, we'll end with 2 hypotheses, one mathematical and one in context. So we can say that there is not enough evidence to reject H0. It was not a significant result. And we do not have enough evidence that the mean strength has been altered. Although for this particular sample, it was a little bit lower than what is expected. It's not significantly lower. Part B of the question asks us, in the light of the conclusion that we've just now made, what would we recommend for the manufacturer to do? So actually, our conclusion says this is just as good as the cement that you've been using before. So if it's cheaper, why not change? So we'll make the recommendation that we'll switch over to the cheaper cement. There is always that thought at the back of your head that actually the sample size is quite small. Maybe we want a larger sample before we make a decision like this, especially with a multi-million-pound company. But for the context of this question and what you're and how you're expected to respond in the first instance, we'll just say that yes, it's cheaper. Let's move and switch supplier.